Well, we're coming up to the end of the line. Not just for this topic, this will be the last lecture on the network simplex method, but also for the whole course, because I took some time to figure out exactly how long the course has been between all of these videos and all the live sessions and exams and things, and I figured this is about the right place to stop for this semester. Maybe back in some in-person semester in the future we'll cover more topics, but I think we've had about enough for this course for this semester. So this is the very last lecture of the course, and that's great because I already have that last day of school sense of excitement. There is quite a bit to get through though, because we talked about being able to perform primal pivots in our network simplex method. We also now have to talk about dual pivoting, and the lecture seems to be called dual pivoting, but we're also going to use this. Once we have dual pivoting, we'll have the ability to put a whole bunch of other stuff together. We want to do that. We want to finally get to the point where I could hand you some arbitrary network instance without a basis, without anything else, and expect you to be able to fully solve it. And to do that, we're going to need both primal pivoting and dual pivoting. So, fundamentally, but what we're going to do first is try and come up with a dual network simplex method. So here we have an example of a flow that is dual feasible, but not primal feasible. And we know that the interpretation of that is that it's dual feasible, but not optimal. Because if it were optimal, it would be both dual and primal feasible. And we saw in the previous lecture that if I hand you a flow that is primal feasible, but not dual feasible, we can perform primal pivots to eventually reach the optimal solution. But what happens if I hand you a flow that is dual feasible but not primal feasible? So we know enough about duality by now to understand that there has to be some dual simplex method if we have a primal one. So if we can do primal pivots, there has to be something that would correspond to a dual pivot. The question is, what is it? And more importantly, for the sake of the lecture, what does it actually mean? So I mentioned in the previous lecture, it's one thing to just sort of read you a list of instructions and say to do a dual pivot, pick this arc, then pick that arc and swap them and recompute. The reason why you're taking a course like this isn't to have somebody read you lists of instructions. Memorizing lists of instructions and following them is what a computer is supposed to do. The goal is not to understand what a dual pivot is, but why a dual pivot works and where we got it from. And that's the point of this lecture. Or I guess at least the early part of this lecture. Once we have the dual network simplex method, we've figured out our dual pivoting operation, we're going to be able to use that to develop a two-phase solution method. So we've seen already when we talked about duality, when we talked about the linear algebraic simplex method, that one way of handling the initialization problem, which is here is an instance of a problem, you don't get some feasible basis to begin with, your job is to find a feasible basis, if one exists, and then solve the problem from there. That's the initialization problem. For regular LPs, we could solve that by solving an auxiliary problem. We could use a primal dual or dual primal two-phase method like we saw in the duality sequence, where we first solve a modified LP that we guarantee to be, for example, dual feasible, and then use the result of the optimal solution of that modified LP to begin solving our original LP. We could try and define an auxiliary problem in the network case, but I think it's much easier, given that we're already going to have dual pivoting and primal pivoting, to instead use a two-phase approach. Given an arbitrary network, we'll find some arbitrary basis, which might be completely infeasible, both primal and dual infeasible, and then we will apply one of the two pivoting strategies. Let's say we'll apply the dual strategy first to find a primal feasible basis, and then we'll apply the primal pivoting strategy to solve that, to actually get to our optimal solution. So that's our goal, is to first figure out this dual network simplex method, and then to apply that to create a two-phase solver. Now, one other thing that's going to show up in the middle, so once we have dual pivots, but before we get to that two-phase stuff, is once we have all the pivoting down, once we've understood intuitively what's really going on there, I want to talk about what the primal and dual problems really mean. I want to talk about a semantic interpretation of the whole problem. We've already spent time talking about interpretations of the variables. So we know, for example, that the primal flow variables somewhat intuitively correspond to the amount of flow being sent across a particular arc. So the arc dB has 6 units of flow. We understand that the dual optimization variables, my y variables, tell us how much it costs to send 1 unit of flow from the root of my tree through the edges of the tree to that vertex. So we have some interpretation of that. We also understand, although it's a little bit less intuitive, that these dual slack variables, so this would be the value ZHE, these dual slack variables give us some sense of the cost differential of the current basis versus a basis that contains the arc with the dual slack variable. So we have an interpretation of the variables, but a question that we should be asking is, I guess we understand what the primal problem is meant to mean, because we designed the primal problem way back in part 1. That is, our goal is to minimize the total cost of distributing flow across all arcs to equalize supply and demand. And we have an interpretation of the primal flow variables and the dual optimization variables and the dual slack variables, but we've never really tried to hack away at what exactly am I solving when I solve the dual problem. So what does the dual objective function actually mean? And we can come up with an interpretation of that. And I actually think, frankly, that that is the climax of this course. That what we're going to get to in the middle of this lecture, that interpretation of the dual problem for the network minimum cost network flow problem, that will bring together all of the pieces of the course. It'll bring it together in a strange setting. That is, it's weird that we're going to finish our course off, that we're going to reach its peak talking about graphs. I'm not complaining, though. I'm obviously deep down, through and through, deep down, I'm a graph theorist. But it turns out, I think, that having this interpretation, being able to develop an LP for a problem, use duality to find a dual, and then interpret that dual in meaningful terms, I think that captures all of the essence of this course. And so I'm really excited to get to that. We're also going to actually see finally a way of tying together all of the strange cases that can arise while we're solving these problems. We saw already what primal unboundedness means in the graph. It would be a cycle whose total cost is negative. We're going to see what dual unboundedness means, and we're going to understand better the connections between unboundedness of one and infeasibility of the other, which we already know has to apply due to the way that the duality theorems work. So first, we need to derive what a dual pivot is. And this is strange. I think this is a place where I had to agonize quite a bit over how to present the material. So for a primal pivot, because we know what the primal objective function means, we can sort of we can push forward with that interpretation to sort of deduce what a primal pivot has to be. It's a bit harder with a dual pivot because, for example, dual slack variables are a little bit less easy to understand. What I decided eventually to do was, before we actually talk about dual pivoting itself, I've got a bunch of little pieces that I want to go through. Some of them are reviews. So this first sequence, as I'm sure you'll notice, this is actually a primally feasible basis. We're just going to talk again about what dual slack variables do and what dual variables do when I perform a primal pivot. And I hope that by doing that, not only is that a nice refresher from the previous lecture, but maybe that puts us in the right mindset to better understand what the dual pivots are. So the first thing I want to do, the first fragment that I want to present is when we perform any kind of pivot, if I modify my basis, what kinds of changes do I have to make? What updates are required? We saw previously, so we know that obviously, okay, here's the flow I have at this step. And if I perform a pivot, I have to make sure that all of the variables, so the flow variables, the dual optimization variables, and the dual slack variables, that they are kept up to date. Of course, I could do this by generating them all again from scratch. We saw back in part 2 of this sequence that you can do that. At any step, with linear time algorithms, we can recompute all of those variables. But we also saw in part 2 and part 3 that there are ways of avoiding having to do a full recomputation. We can only recompute certain values if we can figure out which ones are not going to change. The goal of this set of slides, this first bit here, is just to revisit that topic. Okay, so I mentioned a minute ago, and we might recall from earlier, that these dual optimization variables, so there's my variable y sub d, the dual optimization variables tell us the total cost of shipping 1 unit of flow from the root to that vertex. So to ship 1 unit of flow to y sub d, remember that the costs are actually these values over here. To ship 1 unit of flow to vertex d, I would start at A. It cost me 2 to get from A to B, and it costs me 7 to get from B to D. So of course that's going to come to a total cost of 9. If I want to consider how much it costs to ship something to vertex E, so there's y sub E, well, I would go from A to B to D to E. I actually already know that the cost to get to D is 9, so then I follow this edge with cost 2, and it costs me 11 in total. Now there is this one weird thing that we have to consider, which is if we ever have to follow an edge the wrong way, so follow it backwards, we interpret that as negating the cost. So if I want to ship something from A to F, well, first I have to get it to D, that costs 9, and then I send it the wrong direction across this edge with cost 4, which we interpret to have cost negative 4, which seems a little bit weird. So I've mentioned in previous videos, that seems a little bit weird. I'm hoping that the interpretation we come up with in the middle of this lecture helps to resolve that a little bit. In any case, as a result of this negative 4, the cost to get to F is actually 5, even though it costs 9 to get to D, and then I make some money back by going to F, by following an edge in the wrong direction. Okay, so what I want to talk about is, suppose I perform the obvious pivot here. The primal pivot, there's only one pivot I can perform, and that's this one. I've got one non-basic arc. This has to enter the bases in any pivot I perform here, and it turns out this has to leave. There's only one pivot I can perform. It seems like it's a good idea to perform it, because the basis is primally feasible, but I've got a dual infeasible arc. So if I perform this pivot, maybe my basis will be optimal. And the question basically is, if I perform this pivot, what do I have to update? So if the arc BD, that's this arc here, if it leaves the basis in favor of CD, notice that the dual slack variable on CD has the value negative 5. And what this negative 5 is actually meant to mean is that essentially I can save $5. So the value, the dual slack value, tells me the cost increase of sending flow to D via this arc versus the basis. And so if the cost increase is negative, that means I will save $5 by shipping my flow to D this way versus the way that's currently in the basis. And that's one reason why I'd want to add this arc to the basis, because it will result in a total cost decrease. I'll save some money in my basis, and I want the lowest cost basis when I'm done. So if I perform this pivot, so if I were to remove BD and add CD, then I end up with this. And we recall that if I pull out any arc from the spanning tree, so before I've added my entering arc, after removing the leaving arc, I'm guaranteed, if I had a spanning tree to begin with, that I now have 2 trees. I've taken the spanning tree and I've cut it into 2 pieces, and they will form 2 connected components. Because it was a tree, they have to form 2 connected components. Leaving one arc from a tree will give you 2 separate trees. We also know that one of those 2 components will contain the root. And we saw in the previous video that everything in the same component as the root will actually end up with the same dual optimization and slack values. And the reason for that is because of the way that we compute them. We compute the dual optimization variables starting at the root and working downwards. And so for the part of the tree that hasn't changed, the part next to the root, nothing is going to change in terms of that calculation, so everything can be left as it is. On the other hand, the values for this part, this component here, will change because I'm changing which arc points inwards, and I'm assuming, likely at least, unless it's a degenerate pivot, I'm assuming that I am going to end up with a lower cost and therefore different dual optimization variables. Now, one thing I noticed while preparing this lecture compared to the last one is we talked about these components in the previous lecture, but they're a really big deal in this one. And I realized that we need some way of naming them. And so I experimented with, should I call this C root and C other? And I thought that's not gonna help anything. That's gonna make it even more confusing. On the other hand, the only other names I could think of were just saying, well, the root component can be called component 0, and the other component can be called component 1. And I sort of hate that too. And for some perspective, if you've taken a statistics course, consider, do you remember what type 1 error is? As a student, I thought this was a really dirty trick. I thought, why are they called type 1 error and type 2 error? And I have to preface this by saying this is my personal opinion, but when I got exam questions that were, tell me what type 1 error is or type 2 error is, I thought that was a dirty trick. That was cheap, because having to memorize this completely opaque term to refer to something doesn't really make you any smarter. It doesn't make you understand statistics better. It's an arbitrary name. It almost sounds like gatekeeping. It sounds like people don't want to be inclusive and actually allow the discipline to be accessible. Now, that's just me. That's just my opinion, but I don't like giving arbitrary names to things. Type 1 error and type 2 error could better be called something like false positives and false negatives or something. There's a way, although that's not completely rigorous, there is a way of giving better names to things. The only compromise I could come up with here is we'll call this component C0, but I'll always color code it purple. So we remember that purple goes with the root, and therefore C0 is the root component. C1 will color code that orange. Hopefully that's a good enough compromise, because we're going to need to use these names over and over again in this lecture. Okay, and similarly, I'm going to name the components C0 and C1. I'm going to treat them as if they're sets of vertices. So I could reasonably say that, for example, B is an element of C0, and that's just a notational device. I'm not going to actually do any algebra with these sets, but if I ever want to talk about something being in the set, I want to use set notation. I want to use set membership notation. Okay, so I delete my arc, my leaving arc BD from the basis, and I add the arc CD. That's going to mean that this DEF ends up being my component C1. That ends up being the separated component. And we therefore have to recompute all of these dual optimization variables. Now notice there are no non-basic edges in C1 or attached to C1 besides the one that was my leaving arc. We'll get to that in a few minutes. I've prepared an example here that deliberately doesn't have any other non-basic arcs so that we don't have to worry about too many things at once. So we have to update the values of YD, YE, and YF. And if we do that, so I mean, we could recompute them from scratch. So I noticed that the cost of getting from vertex A to vertex D will be, oh, I don't actually have it up in front of me. So if I take the arc AC, that's 3. If I take the arc CD, that's 1. So I should expect, for example, that this is going to have a total cost of 4. I could go through and do that update for every vertex, and I end up with this. What we should observe, though, is if I look at the updated values and I look at the original values and I consider their difference, I might notice that what I ended up doing to compute the new value was basically just add this dual slack value, -5. I just add this to each value. And that gives me my updated dual optimization variable. Now, if you go look at the equations for the dual LP, it becomes clear why this is the case. It's basically because the update to vertex D definitely involves this entering arc, and the entering arc has a cost that's 5 lower. The update for every other vertex below D in the component C1 is going to piggyback on the change to D. Nothing else has changed inside of C1. So whatever change applies to D is going to propagate through the remainder of C1. And so that's one reason why maybe it's a little bit intuitive that the adjustment I'm applying to every vertex is the same because I've only made one modification to my basis. And it turns out the adjustment that I perform will equal the magnitude of this dual slack variable. Now, the way that I make the modification could depend on which direction the edge points. So there is one nuance we have to observe, which is that we could be working with a basis where the edge that we're removing, or the edge that we're adding or removing, points in the other direction. In which case the modification would be the reverse, like it would be subtracting instead of adding. But the magnitude of the change is the same as this magnitude, so it's -5. So in this case, the edge that the entering edge points into C1, and therefore the adjustment that I make will be to add the old dual slack value to each of the dual optimization variables. So 9 plus -5 is 4, 11 plus -5 is 6, 5 plus -5 ends up being 0. Now, more formally, if my entering arc is arc ST, the change in the dual optimization variables inside of C1 will be one of the following. So if ST, so in this case, this would be vertex S, this would be vertex T, and there's ZST. Notice how the edge ST points into C1. In other words, the destination T, that is a part of C1. If that's the case, we have this situation here. We adjust our dual optimization variables by adding ZST to every single the current value of each dual optimization variable. Now, in the event that we had a situation more like this, where we've got, where am I going to draw? So here's C0 and here's C1. If we have a situation where the arc that's entering points away from C1, in other words, we've got our arc is ST, and vertex S lies in C1, and vertex T lies in C0, that's this case here. In this case, the adjustment to the dual variables inside C1 will be negative ZST. So there's a sign flip if the direction of the edge is opposite to the example that we have up on the slide. That's it though. The adjustment itself, the magnitude will be the magnitude of ZST. It's just a question of whether we negate it first. Okay, so now we can take that example and embellish it a bit. What if we consider this version, which has a few extra non-basic edges? My goal here is to think about what adjustment is needed to the dual slack variables. And we already know what we're going to do with the dual optimization variables if I pivot in this arc here. So if I remove BD and I add CD, we already know what's going to happen to YD, YE, and YF. The question is, what am I going to end up doing with these Z values? So this would be ZEB. How do I adjust those? Notice that when I construct my component C0 and C1, so there's C1 down here, notice that there are some non-basic edges that lie entirely inside of C1. There are some non-basic edges that point outwards, and there are some non-basic edges that point inwards. Now we know from the previous lecture that if there were non-basic edges that were entirely in C0, so for example BC, which is in C0, they wouldn't need any adjustment at all, for the same reason that we don't adjust the dual optimization variables in C0, because the computation won't change, and because the dual slack variables are based on the dual optimization variables of their endpoints, they won't change either inside of C0. Okay, so we already know, therefore, that after I change basis, only those edges where at least one endpoint lies in C1 will need to be updated. So only these non-basic, well actually it's all the non-basic edges currently shown, only these edges will need to be updated. The question is, what is the update? Can we derive some formula for the update? And it turns out that there's actually, we'll notice that the only dual slack variables that will change are going to be ones, edges that I'm going to use the term bridge between components. In other words, if I have C0 and I have C1, only those arcs that cross between C0 and C1 will need their dual slack values updated. Any arc that's entirely in C0 doesn't need to be updated. We already know that. It turns out, though, that any arc that's entirely in C1 also doesn't need to be updated. And we know from the previous parts that this is the formula to compute a particular Z value. So if I want to know the dual slack value for arc UV, it's computed according to this formula here, where the cost is a constant because it's part of our input, and of course these are the dual optimization variables for the two endpoints of the edge. So one thing to notice is, if I'm looking at an arc that's entirely contained inside of C1, well, what do we know about the change to the dual optimization variables in that case? Well, we know that each dual optimization variable, so let's think about the old value of Z, this would be ZFE. Okay, so ZFE is equal to the cost of edge FE, which I now have to go get, which is 2. Okay, the cost is 2. That's going to be plus the Y value of the source, which would be F, minus the Y value of the other endpoint, which would be E. If we compute that in the original graph, we end up with 2 plus YF would be plus 5, and then minus 11. Okay, so 2 plus 5 this would be 7, minus 11, which is equal to negative 4. Okay, that makes sense. We have negative 4. And the reason I wanted to write the formula out explicitly is because maybe it's not obvious how to solve. I mean, I want to move the terms around to make it convenient. Okay, so that's the value of ZFE in our old basis. So both E and F are contained in my component C1. So both of them are going to experience the same change in their dual optimization variable. Let's consider the new value of ZFE. Well, we can just use the old value and rewrite it in terms of the change. So it's going to be the new value of YF will be the old value of YF minus 5. So because we know the adjustment will be minus 5. And the new value of YE will be the old value minus 5. And you might notice that because of the plus and minus on the two terms, because I have plus YF minus YE, if both F and E experience the same adjustment in their dual optimization variable, then the value of ZFE won't change. This negative 5 will get canceled out by, well, this will end up being a positive 5 over here. And that means that if you have an arc whose endpoints lie entirely in C1, the change to the dual optimization variables on each endpoint will basically cancel out any possible change to this. And that means that the dual slack variables for any arcs that are entirely inside of C1, those won't change. And so we can use similar logic to try and derive the change to everything else. But what I just illustrated was the first bullet point here. If I'm considering how to modify my dual slack value ZUV, then the first question is, do both endpoints lie in the same component? Are both u and v in C0, or are they both in C1? If so, then we do nothing. The value of ZUV will not change. Otherwise, there are two cases, and the two cases correspond, just like earlier, to those two cases. There's C0, there's C1. We know now that the only edges for which the dual slack variables change are edges that bridge the gap between C0 and C1. But there are two ways to do that. I could bridge the gap from C0 to C1, or I could bridge the gap from C1 to C0. And it may not surprise us to learn that the adjustment is opposite for the two directions. So suppose that I have, I really wish I'd left more space on my slide for a drawing. Suppose that this is my arc ST. Or to put that a different way, I'll just move these around. So that means that my entering arc here is, let's see, so there's vertex T. So suppose my entering arc points from C0 to C1. It turns out that regardless of which direction the entering arc points, the two cases correspond to whether the arcs that I'm updating point in the same direction or the opposite direction to my entering arc. So suppose I consider some arbitrary arc UV. I've got an entering arc, it's arc ST. If I consider some arbitrary arc UV, and actually in this case, it doesn't even matter which component is which. I know my entering arc bridges from this side to this side. If I consider an arc UV where the vertex U is in the same component as the vertex S, which is to say that the arc UV and the entering arc ST point in the same direction across the two components. If that happens, the new value of ZUV will be this. I will subtract the dual slack value for ST, my entering arc. On the other hand, if I'm dealing with a case where if I'm working with some arbitrary arc UV where U lies in the same component as T, which is to say that that the arc UV points in the opposite direction from my entering arc, in that case, the new dual slack value will equal this. So I'll add the value of ZST. So again, notice the sign flip. We saw already that if our leaving arc or our entering arc points in one direction, then the dual optimization variables get updated one way. If it points in the other direction, the update is basically negated. The same thing happens with these two directions of edges. Edges that point in the same direction we will subtract. Edges that point in the opposite direction, we will add. You might already notice the first signs of something that we're going to need later in the dual pivoting procedure. We know that in pivoting procedures, we often consider carefully these cases where we're subtracting a number, because we know that if I subtract the wrong number, I might end up with this variable going below 0. And it's often using these negative signs that we're able to figure out what the limits are on our entering or leaving variable. And it turns out this will indeed be the case. We are going to end up seeing a situation where this actually happens, where this actually determines what our choice of entering arc has to be. We have to choose an entering arc so that none of these potential equations end up going negative. Okay, so here are updated dual slack values. So in this case, I have, here is my entering arc. It's the arc CD. I guess we'll draw a box around the component. Okay, so there's my component C1. My entering arc CD points into C1. Okay, and we know already that anything in the same direction of CD, I'm going to subtract this value. And so this edge here is in the same direction as CD. So I subtract, so 7 minus -5 will equal 12. Okay. Any edge that's entirely inside of C1, like this edge, doesn't change at all. So it's still -4. Okay, that looks good. And finally, this edge here points in the opposite direction. If it points in the opposite direction, then I add. Okay, so if I add -5 to 16, I get 11. All right, so I've seen all three cases here. I've got edges that point in the same direction, edges that point in the opposite direction, and edges that are entirely contained in C1. Now remember, the key thing here is I'm not saying that every time an edge points from C1 to C0 you add. I'm saying if the edge points in the opposite direction of the entering arc, then you add. If it points in the same direction, then you subtract. Okay, so in a dual pivot, we know already the way dual pivoting works. We expect that we have a basis that is dual feasible and may not be primal infeasible. Now, of course, if it is primal feasible, then there's no point in pivoting, because if it's both primal and dual feasible, we're at an optimal solution. So suppose that it is dual feasible but not primal feasible. Well, then we want to do some kind of a pivot. In a traditional dual pivot, we like to conceptualize a dual pivot as performing a, we usually phrase it in terms of the primal pivoting strategy, which is we're going to choose our leaving variable first. In our dual pivot, we choose some primal infeasible basic arc and pull it out of the basis. And then we choose some entering variable to restore the basis and maintain dual feasibility. It's really important that we maintain dual feasibility because if we lose that, we can't perform any more dual pivots. Now, we saw before, obviously when we're choosing an arc to begin a pivot, so an entering arc in a primal pivot or a leaving arc in a dual pivot, the exact choice, if I've got multiple possibilities, which I definitely do here, the exact choice is up to a pivot selection rule. In this course, unless I say otherwise, so unless I deliberately don't follow this rule, in this course, if I ever perform a pivot, I hope I was clear about this in the previous video, but I'll make it extra clear now. If I ever perform a pivot without either insisting on doing a specific one or stating what rule I'm using, we are going to assume that we're using the largest coefficient rule. The network equivalent of the largest coefficient rule is sort of the negation of that, I guess, which is that the largest coefficient in the dictionary form of this LP right now is actually this. In other words, because we're used to framing our variables a certain way, we'll end up with the largest coefficient in the dual LP right now is actually positive 14 because of the way that we always negate when we take duality. So this is would be the entering arc under the largest coefficient rule. So obviously that's just a pivot selection rule thing, but in the examples later in this lecture, when you notice that I keep choosing pivots, that is how they are being chosen. They're just being chosen based on this largest coefficient rule. So the smallest negative value, strangely, that is the analog of the largest coefficient rule for both the primal and the dual case. Now, on the other hand, of course, any primal infeasible arc, including this one or this one or this one, could be the leaving arc. It's just up to the pivot selection rule. So for example, I could choose this arc as my leaving arc. And for the sake of this example, I am going to try that, just for a few slides, because I think it makes the example easier to visualize. But of course, the pivot selection rule could pick any of those primal infeasible arcs to use as the leaving arc. And we don't know in general, just like any other LP, we don't actually know what's going to result in the smallest number of pivots. I mean, the largest coefficient rule is a good heuristic, but it's just a heuristic. So suppose that I choose this arc DG as my leaving arc. I want to perform a dual pivot, so I choose my leaving arc first. If I do that and I delete DG from the basis, well, I now no longer have a spanning tree. I've deleted an edge from a spanning tree, and so predictably I have my two components, C0 and C1. All right. And so clearly, I think I already have some hint as to what I need to do to finish my dual pivot. And my goal in this sequence is, instead of just saying, here's a list of things to do for your dual pivot, I want to see if we can deduce them all from scratch, just like with primal pivoting. So one thing we know is that when I choose my entering arc, whatever I choose, it has to result in me having a basis when I'm done. I can't continue this problem if my basis isn't valid. So I know that my entering arc has to reconnect these two components. It has to somehow bridge between C0 and C1. So I can already narrow down what my possible entering arcs are going to be, because I know that whatever it is, it has to restore my spanning tree. So the question, of course, the broad question is, which non-basic arc should be my entering arc? I guess I got a bit ahead of the slides here. What I just said is equivalent to saying this arc definitely is out of the question. Because if I look at that, if I add the arc EB, I'm not only not going to have a spanning tree when I'm done, I'm also going to have, I'm just going to have this cycle, which of course isn't, I mean, a spanning tree can't have a cycle, and it also has to be connected. So I've got a lot of problems if I do that. That means I can rule out this arc here, and I can rule out this arc here. The only arcs that are valid, that are viable candidates, are ones that bridge between the two components. So I've already managed to rule out a few possibilities. And we're going to see in a few minutes, I'll be able to rule out a lot of other ones too. In particular, because of the discussion I had a minute ago about how there are various arcs that bridge the components, but the update I perform on dual slack variables will be different for arcs that go this way. Now that's the leaving arc, versus arcs that go this way. And it turns out we'll actually be able to rule out all of the arcs pointing in one direction, and that'll allow us to narrow things down even further. So if this were the lecture about primal pivoting, we would do some reasoning about how to select entering and leaving arcs by just thinking about the objective function. We would look at the primal objective function. We would say what is likely to increase, or to, in the primal case, it's a minimization problem, to decrease this objective value. That's the way that we sort of reasoned our way through much of the primal pivoting derivation. The problem is that the dual objective function is a bit obtuse. It's a linear combination of the y variables. Now, those are impacted by the z variables, but it's not really obvious how we're supposed to interpret that. And so it's not very intuitive for the purpose of deriving dual pivoting. So what I'm going to do instead of what I did in the primal case is I'm going to try and use what we know about the rest of the problem, so primal flows and the way that spanning trees work and things. I'm going to try and use that to deduce the behavior. I'm not going to go directly to the dual objective function. Now, that said, somebody owes you an explanation of what the dual objective function really means. So I will talk about that. I am going to talk about the meaning of the dual problem later in this lecture. I'm really excited to finally get there, hopefully in the next hour at some point. But for the sake of deriving our dual pivoting procedure, I don't think it's that productive just yet. So here is a shopping list. Here is a list of things I think we can agree, based on what we know about just about pivoting in general. Here are a list of things I think we can agree have to hold, both before and after the pivot. And one note, I feel like it's an invariant, but this needs to hold both before and after anyway. So saying the basis must be dual feasible, the basis has to be dual feasible up here too, because if it's not dual feasible, I can't perform dual pivots. I'm just going to take that one for granted. We know by now that we can't perform pivots that mean anything in the simplex method on an infeasible basis. So my hope is that this set of requirements, which I think we can all agree upon, that if I use these requirements and I reason about them, like I look at them in pairs and things, I might be able to rule out enough possibilities to derive what a dual pivot should look like. So let's go through them. The first thing is, if I'm performing a dual pivot at all, it means that my basis has to be dual feasible but isn't primal feasible. Because if it were primal feasible, it would be optimal, so I wouldn't need to perform a pivot. So therefore, there has to be at least one primal infeasible arc, and it makes sense that will be my leaving arc. There could be multiple choices, but certainly my leaving arc will have this property. It'll have a primal flow that is negative. It will be primal infeasible. Now, the second thing to observe is that because my basis is dual feasible, every z variable will be non-negative. So this is a consequence of my basis being dual feasible. There are no choices of entering arc that don't have this property if my basis is dual feasible. So the z value of my entering arc has to be non-negative. Okay, that's before the pivot. Now, what do I want? I want to choose my entering and leaving arcs so that when I'm done the pivot, all three of these conditions hold. Okay, the first one is I want to make sure that my leaving arc, so my leaving arc was basic before the pivot and is now non-basic. If it's non-basic, then obviously I can't push any flow across it, so x has to equal 0. Because I want to make sure that dual feasibility is maintained, I should expect that z, the z value of my leaving arc, once it's out of the basis, has to be non-negative. If it goes negative, my basis isn't dual feasible, then I'm in trouble. Similarly, my entering arc was outside the basis before the pivot, and once I've performed the pivot, it's in the basis. If it's in the basis, then by complementary slackness, this, the z value for it, has to equal 0. And if all goes well, and this is, it turns out, I say ideally here because I don't want to assume too much. It turns out this is actually a guarantee we can expect. If all goes well, I want, when my pivot is done, for the entering arc to be primal feasible. I don't want to end up back in the same boat. And we've seen already that in the regular simplex method, if I perform a pivot, when I'm done, it is reasonable to assume after a dual pivot that the entering variable is primal feasible. The same way that in the primal simplex method, if I perform a primal pivot, so let's say I have the variable x3 enter the basis and the variable x7 leave the basis. We know already, because it was a midterm question, frankly, we know already that x7, when it leaves the basis, its objective coefficient will be negative. So that is to say, it will be dual feasible. The same logic applies for the dual primal case, which is once I perform a dual pivot, the arc that I put in the basis will indeed actually be primal feasible. I only say the word ideally here because I can't as easily guarantee see that in a graph theoretic sense just yet, but that is something we need. If we don't have that, our dual pivoting procedure may not end up being very productive. And we're going to use this to seal the deal. This will be the way that we figure out exactly what we have to choose. Now, finally, the basis that we come up with after the pivot has to be dual feasible. These two conditions certainly imply that the entering and leaving arc end up dual feasible, but just in case there was any doubt about this, no other arcs can be allowed to turn infeasible for the dual. So we have to choose our entering arc wisely so that those equations that we already saw, where we adjust for other arcs, the adjusted value of the, so z uv prime, for a particular other arc that isn't our entering arc, I guess I'll call this zpq. If I look at some arc PQ that isn't my entering or leaving arc, I want to make sure that its updated dual slack value never goes negative. It has to be positive. And we know already that the formula to compute the new dual slack value could be negative or, it could involve a subtraction or an addition, depending on which direction the edge points. I'll observe that because ZST has to be greater than or equal to 0, if I'm adding these two things together, there's no way this is not going to be non-negative, because ZPQ has to be non-negative to begin with, and ZST has to be non-negative to begin with. The problem is if I'm subtracting, if PQ and ST point in the same direction, we subtract in the same direction. If that happens, I have to make sure I choose ST wisely so that ZPQ doesn't end up going negative. That's going to be a big deal. That's going to dictate our choice. Now, the slides are now going to say the same thing I just said, I think, but maybe more clearly. If we take a look at any two of these observations, or three of them at a time, we can deduce quite a few things. Okay, the first thing is, we, by definition, have defined these two components, C0 and C1. And we know that our leaving arc carries flow in one direction between C0 and C1. We don't care which direction it is. It could go backwards from C1 to C0. It could go forwards. We've chosen a leaving arc, and we've separated the spanning tree into two components based on that leaving arc. So we need to make sure that when we're done, our spanning tree is restored. And therefore, we have to choose some entering arc to be one of the other arcs bridging this gap. So we know, and we saw this already, we know that our entering arc has to bridge between C0 and C1. So the next question is, which direction should it be bridging? So the entering arc will have to be dual feasible because every non-basic arc is dual feasible. In a dual feasible basis, there aren't going to be no negative Z values. And we also expect reasonably, so I say expect, just like I say ideally, we expect that our entering arc will be primal feasible when we're done. Other arcs might not be. The basis has to be dual feasible, but we may not be done solving the problem yet. So there could be other primal infeasible arcs, but we at least expect our entering arc to be primal feasible when we're done. And I'll explain in a minute why it's reasonable to expect that in any practical case. So there are situations where we can't guarantee that, but it turns out those correspond to unboundedness, which is why we can just handle that separately. And so because we know, if I look at C0 and C1 again, I'm just going to keep redrawing the same diagram over and over again. Suppose this is my leaving arc. It goes from C1 to C0, and I chose it as my leaving arc because it's primal infeasible, and that means that it has a negative number. Let's say -3. What does this mean? Well, what this means is that apparently to maintain flow balance, there have to be 3 units of flow going from C0 to C1. And the way that that was done in the basis that I had before the pivot was to send 3 units in the wrong direction across my leaving arc. So what I know is that when I delete my leaving arc from the basis, I still need to find a way of sending 3 units from C0 to C1. And I want the result to be primal feasible. So obviously, if I choose an arc that points in the same direction as my leaving arc, it's going to end up with a flow of -3, which just brings me back to where I started. I want to choose an arc that gives me primal feasibility, which means I want to choose an arc that points in the right direction. If my leaving arc has a negative number, I want to choose an arc pointing in the opposite direction so that I can send the same amount of flow, because the amount of flow that goes from C0 to C1 is going to be the same no matter what. I want to send the flow in the right direction. So I want to choose my entering arc to have the opposite direction as the leaving arc. That way the entering arc will be primal feasible. Now, the reason why I keep referring to the fact that I say this is only something I want ideally, is there could be a case where there are no arcs that meet this criteria, where every single arc points from C1 back to C0. Now, we'll see later, it turns out that's actually an unbounded dual. And so we'll come back to that and address that later. For now, though, we will say, let's assume we have an arc pointing in the right direction and choose that. That way we'll get a primal feasible result. So our entering arc will point in the opposite direction as our leaving arc. Now, when we're done, I have to make sure that my basis is still dual feasible. I've found a way of ensuring that my entering arc is primal feasible, but I have to also make sure that my leaving arc and every other arc bridging the two components is still dual feasible. Or, I mean, moreover, every arc has to be dual feasible. Here's the diagram again. Although we know that the only arcs that are going to change, the only arcs whose dual feasibility could be in jeopardy, are the ones bridging the gap. Because every arc inside of a particular component will have no change to its dual slack value by the derivation we came up with earlier. So what I want to do now is think, okay, I'm choosing, if my leaving arc points in this direction, so if this is my leaving arc, my entering arc has to point in the opposite direction. I now have to make sure that among all of the possible entering arcs, the ones that I could choose that point in the opposite direction, I choose an entering arc that results in the basis continuing to be dual feasible. And here's where I can bring in those equations that I used earlier to try and deduce what arc I want to choose. And so if we take a look at this, so I'll just redraw it. If I look at some arbitrary arc, I guess I'll still call it PQ. If I look at the new value of ZPQ for some arc PQ that bridges this gap, and I consider my entering arc ST, the new value of ZPQ will be, if PQ points in the same direction as my entering arc, it'll be this. ZPQ minus ZST. If my entering arc points in the opposite direction of PQ, the new value of ZPQ will be this. Maybe it's clear all of the arcs that point in the opposite direction are not in jeopardy of going negative. Their dual slack value will never go negative as a result of this. So the only arcs I'm concerned about are the arcs that point in the same direction as my entering arc. So just to be clear, the same direction as the entering arc, not the leaving arc. The entering arc, any arc that points in the same direction as my entering arc will get adjusted like this, which means I have to choose my entering arc carefully to make sure that this can never go negative. And if you stare at it for a minute, you might notice what that seems to be telling me is I choose my entering arc to have the opposite direction of the leaving arc, but among all arcs with that property, it should have the smallest dual slack value. So there's no way that the dual slack value of the entering arc is bigger than any of the arcs parallel to it. And so maybe we can see already, the slides are now going to go through this in a couple of different ways. We're going to see already how we can now narrow down our choices of entering arc using all of these properties. Okay, so basically the question is, suppose that we don't have a dual feasible basis when we're done. So I have some edge PQ that does bridge C0 and C1, and it's dual infeasible after the pivot. So what I just described is an equational way of coming to the conclusion. I want to talk now about a more interpretation-based way. Suppose that we have some edge that's dual infeasible. Okay, here it is again. So there's C1, there's C0. I've got some edge, so there's one of the endpoints is P, one is Q, and ZPQ is less than 0. What is this telling us? Well, we know already that ZPQ is supposed to be the potential cost increase by using the edge PQ instead of some other edge that's currently in the basis. If I notice that ZPQ is negative, what that's telling me is that the arc PQ is a lower cost route. If I used PQ instead of whatever I'm already using to go between C0 and C1, I would save money. So the arc PQ is a lower cost route between C0 and C1. If I want to prevent any of these bridging edges, any of the edges between C0 and C1 from becoming dual infeasible, from having this situation occur, I want to make sure that whatever edge I bring in, my entering arc, is the lowest cost route. That there is no other arc that is lower cost, because if there's an arc that's lower cost, it will end up with a negative dual slack value. And that's another way of reaching the same conclusion I already reached, which is that I want to choose the smallest dual slack value among those that are pointing in reverse, because if among all of these arcs I choose the one with the smallest dual slack value, I'm choosing the one that will result in the smallest increase to my total cost. In other words, I'm choosing the lowest cost route. Now, we can actually also see that by just looking at the equation. So I already did this. I wrote the equation on the slide. I got ahead of myself. So again, that wonderful last day of school energy is sort of getting the better of me here. It turns out the slides which don't have the same last day of school feeling. I'm sure the slides have a horrible morose last day of school feeling because unlike me, at the end of the last day of school, I get to go out and enjoy my summer. The slides at the end of the last day of school sort of cease to exist, I guess. They face some bizarre existential crisis because the slides aren't needed after the last day of school, which is actually sort of sad. So poor slides. No wonder they want to drag things out. If we look at the equations we saw earlier for how to compute these dual slack variables, we will observe that we have our leaving arc points in one direction and our entering arc points in the other direction. So we already know that has to be the case. And we know that there could be a bunch of other parallel arcs to the entering one. And we know because of the equations that define the adjustments to dual slack values, all of the arcs in the same direction are subject to this equation to recompute the value. And actually, I think the next slide gets at that, yeah. So we have a few ways of thinking about that. One of them is, actually, I'll go back and forth. So one of them is, first, any arc that points in the same direction as my entering arc needs to have a larger dual slack value. Because if it doesn't, then when I subtract off the dual slack value of the entering arc, I'm going to have my dual slack value for the edge UV go negative. That's no good. That's obviously not allowed. That's dual infeasible. So that's a reason why the entering arc has to have the smallest dual slack value among all of the possibilities, the smallest dual slack value. There's also this other interesting observation, which is that a minute ago I said something like the leaving arc points in one direction and the entering arc has to point in the other direction. We can actually see why this has to be the case. We've already proven that it has to be the case by sort of interpreting the problem. These equations actually tell us that too. So consider the fact that my leaving arc, the arc UV, suppose that UV is my leaving arc, it's basic before the pivot, which means that the value of ZUV before the pivot has to equal 0. So here's my leaving arc, it points in this direction. If my entering arc points in the same direction, then the adjustment formula to my dual slack variables still applies to my leaving arc, which means that my leaving arc, if it points in the same direction as my entering arc, the adjustment that I have to perform to the leaving arc will be this one. And I know that ZUV is equal to 0, which means that my entering arc is pretty much guaranteed to make the leaving arc go negative if I'm not careful. That is more evidence that I have to choose as my entering arc an arc that points in the opposite direction, because that's going to mean that the adjustment I perform to the Z value of my leaving arc is this one, which obviously will not result in my leaving arc having a negative Z value. So that's one more way of seeing that my entering arc has to point in the opposite direction. Okay, and then finally, I'm aware of a notational snarl here. I'm using UV in the wrong way. I'll just correct that on the slide. The arcs Z, we'll call that ZPQ. Okay, and this is the observation I made a minute ago. All of those arcs that point in the same direction, so here's my entering arc here, and so this would be T, and this would be S. If I consider all of the arcs that are parallel to it, so that would be PQ, so this would be ZPQ would get attached to this, and ZST would get attached to this, I want to make sure that ZPQ never goes negative, which means I have to make sure that all of the arcs parallel to my entering arc have larger, or that the entering arc's dual slack value is less than or equal to all of the dual slack values of the parallel arcs. So one way or another, I've presented now, I guess, 3 different ways of attacking the problem. One way or another, we actually now have a dual pivoting procedure that we were able to converge on essentially by observation. We were able to use what we already understand about the interpretation of the problem, about the equations for computing dual slack variables and dual optimization variables. We were able to put all of that together and work out pretty much what we have to do in a dual pivot. And so just to go back to our earlier example, suppose that I insist on using this as my leaving arc. Okay, so what I'll do, just like in the previous lecture, is if I consider now the arcs that form the bridge between C0 and C1, they are all of these arcs here. And I'll color them differently depending on which direction they point. The arcs that are parallel to my leaving arc are in light blue. And just like in the previous lecture, those are irrelevant because we know already that our entering arc has to point in the opposite direction. So it has to be one of these 3 things. And we know now that it pretty much has to be this one. The entering arc has to be GE. The entering arc in a dual pivot is the arc oriented in the opposite direction to the leaving arc that bridges the two components with the smallest dual slack value. So it'll be GE. And so the slides will eventually get there. I sort of understand the slides issue here. The slides want to go on, and they know that when the course is over, the slides are over too. Okay, so the entering arc is going to be GE. And so we actually have a dual pivoting procedure. So the first thing we do is we choose some primal infeasible basic arc. We'll call that L. That's our leaving arc. We then figure out what are those two components. Please let this be the last time I have to draw this diagram. What are those two components formed by deleting L from the basis? Keeping in mind, L could point from C1 to C0 or from C0 to C1, but it is the connecting arc. When I delete it, what are the two components? What are C1 and C0? Now I locate all of the edges that bridge C1 and C0 in the opposite direction as my arc L. So in that case, that would be this direction. And then I choose my entering arc to be among those opposite directed edges, the one with the smallest dual slack value. And then, once I have that, I now have my entering and leaving arc. Here is the actual pivot itself. If my leaving arc, which we know to be primal infeasible, if it carried -3 units of flow, then my entering arc has to carry the same amount of flow because balance has to be maintained. My entering arc, though, points in the opposite direction, so it carries +3 units of flow. So what I'm really saying here, I know this word negation seems a bit weird. The real reason for that is because L and E point in opposite directions. When I negate -3, I end up with the primal feasible value, +3. Okay, so I do that. That's the flow I send across arc E. And then I update my dual variable values for all the vertices in C1. I can leave C0 intact. And I update the dual slack values for all of the edges that bridge between C0 and C1. And so that is my dual pivot procedure. So we'll go back to our initial example from an hour ago, which is, starting from this dual feasible basis, let's find the optimal solution using the dual network simplex method. So I can't use primal pivots because I don't have a primal feasible basis, but I can use dual pivots. All right, so the first iteration, and in this example, I am going to use the largest coefficient rule. So here I choose AB as my entering arc. So let's see what we know. As far as I can tell, that separates the graph pretty dramatically. So this is C1, and A is just sitting in C0 by itself. We know that A will always be in C0, because C0 is defined to be the component containing the root, which is A in this course. Okay, so these will be C0 and C1. What are the edges that bridge in the opposite direction from the arc? So AB bridges like this. So what are the arcs that bridge in the opposite direction? Well, it looks like DA bridges in the opposite direction, and that's it pretty much. Okay, so if I actually categorize that, okay, yeah, DA is the only choice for my entering arc. So of course now it is my entering arc. I then just take the flow that I was sending from B to A in reverse, and I send it in the forward direction from D to A. All right. Okay, so now my total cost is -4. Okay, and of course, wait, total cost, how is it -4? Keep in mind that because my basis is not primal feasible, the cost of sending flow is going to be completely illogical. I should only expect this cost to make sense once I actually have a primal feasible basis. The other thing we should keep in mind is that the primal problem is to minimize the total cost of the flow. The dual problem is some kind of maximization problem. We'll talk about it more in a few minutes, but it's a maximization problem. So we should expect this cost to go up as we perform our dual pivots. Okay, iteration 2. Well, looking what we have here, this is the smallest primal infeasible value, so we choose this as our leaving arc. So where does that leave us? I think that disconnects the graph like this. There is C1, and everything else is C0. And I think I'll just draw C1 by itself so that I don't make the diagram too cluttered. Okay, so my leaving arc points towards C1. What are the arcs that point away from C1? I think it's actually just CH. I can't see anything else. So I suspect then that CH is going to be my entering arc. And yeah, sure enough, there it is. So if I look at the arcs that actually bridge the components, yeah, CH is the only one that points in the reverse direction from DB. And so I had -8 running across DB, and so now I send +8 across the arc CH. And I end up with this. Okay, so now my cost, whatever, it's now 68. It's gone up. But that makes sense because I'm working my way towards a primal feasible flow. Okay, I'm not done. I have primal infeasibility still, so I choose DG as my leaving arc. Okay, so DG will separate the graph. I guess this will be C0. And everything else will be C1. Okay, so DG points away from C0. And the only thing I can think of that points into C0 is the edge FD. I can't see anything else. Okay, yeah, and sure enough, there it is. So FD, therefore, has to be my entering arc. Now, while we're on the subject, since we have this visualization up, just like back in the lecture on primal pivoting, we might have thought while we're doing the first couple of examples, hey, what's going to happen if all of the arcs that I can consider are blue? What if all of them are the ones I'm supposed to ignore? What if there are no arcs pointing into the component when I'm looking for arcs pointing into the component? And it turns out, sort of unsurprisingly, that's going to be the case where things are unbounded. Now, the question we'll have to ask is, why is that the case? Like, what does unboundedness in the dual actually mean? And I will get to that later. But if we ever end up with a situation where we have a component where the leaving arc points in one direction and there simply are no arcs in the other direction, that actually is unboundedness. Okay, so iteration 3 is over. My cost has gone up further, but I'm not done yet. I still have at least one more pivot to do, and it's going to have the leaving arc CE. So when CE is my leaving arc, you might notice this is C1. E is just a leaf, and so C1 is just E by itself. The leaving arc points towards C1, so I want to choose my entering arc to point away from C1. And actually, this is a good, before we do the pivot, I want to take a minute to just study this one case. Notice if we stare a bit at what's going on at vertex E, we can understand why it's primal and feasible. Vertex E has a net supply. It has extra flow, and yet the only way it's connected to my network is via an edge pointing in. So for E to get rid of all of its flow, it has to send it backwards across an edge. So it makes sense I'd want to choose an edge attached to E in my basis that points away from E, and that's exactly what I'm doing with my pivot. So my leaving arc points into C1. I want to choose the smallest dual slack value on an arc pointing away from C1. And actually, just like in the previous examples, I think my choice is dictated. It has to be this one. All right, so I will choose my entering arc to be EB. I will assign the 2 units of flow that were previously sent in the wrong direction along my leaving arc. I will send them along my entering arc, and I end up with this, and it turns out that this is optimal. And the cost is 264, which is apparently meaningful, I guess, but obviously we know we don't really care too much about the total cost until after we're done and we have the optimal solution anyway, but there it is. I'll have another example here. This is a bit shorter. So we start from this. This is our familiar graph from the previous lectures. This is a basis that is dual feasible but not primal feasible. And the question is, can we find an optimal flow using, again, a bunch of dual pivots? Okay, so the first question is, what will our first pivot be? I think our first leaving arc will be HG. Oh, sure enough, there it is. We'll notice that, of course, that puts G in C1 by itself. And, I mean, I wonder what the entering arc is. So the entering arc obviously has to be this. There's just no other choice. So sure enough, there it is. We will now take the 10 units of flow that were being sent away from G in the wrong direction, and we will send them in the right direction, across to vertex F. All right, our cost will be 170, I guess. Remember that as we go forward, the cost will keep going up and up, because in exchange for fixing the primal feasibility of edges, we're going to have to pay more. It costs very little to send flow in reverse across this edge, but I'm not allowed to do that. So it makes sense that as I fix up the directions of flows, that my cost will increase. My next leaving arc will be AE, and this does this thing we saw before where A is just stuck in a component by itself, and so we have to choose an arc that points into the component because the leaving arc pointed out, and that clearly has to be this arc here. So we choose BA as our entering arc, we assign it 6 units of flow, and we keep going, and it turns out we're actually now optimal. The total cost is 224, and you might go back and check the previous lecture where the total optimal cost was also 224. So that was the dual simplex method. We now know how to perform dual pivots. But what is the dual? I mean, what does it mean? We're used to by now this idea that every LP has a dual, and we know that there are some profound connections between the primal and dual. But we've just spent 3 lectures going into minute detail about finding a meaning for everything. We found a meaning for our primal flow variables, that is to say the volume of flow across a particular arc UV. We found a meaning for our dual optimization variables, which is the total cost of shipping 1 unit from the root to vertex V. We found found a meaning for our dual slack variables, which is the cost differential of shipping flow to vertex V via this arc, as opposed to directly through the basis. And so maybe we should try and find a way of deriving some deeper meaning from that dual problem. And the way I'm going to do that is I'm going to use an economic interpretation. So there are lots of ways to interpret problems, but we should appreciate that the minimum cost network flow problem does seem inherently to be a bit of an economic problem. That is, you have a bunch of flow, you want to spend as little money as possible distributing it to where it's needed. And we have a pretty intuitive interpretation of what the primal LP means. My goal is to construct a similar interpretation in terms of economic considerations for the dual LP. And the reason I'm doing this is to try and attach some real meaning to concepts like unboundedness. We could come up with other interpretations besides economic ones, but the economic one I think is pretty intuitive because that's how we derive the LP initially. So first off, what is the economic interpretation of the primal problem? And it's a logistics problem, which is to say, you run a company that distributes some kind of merchandise. Maybe it's the power company, maybe it's water, maybe it's oil, maybe it's sofas. And your job running this company is to convey this resource between different sites, between different locations, such that you can meet your internal needs. So an example would be, you have a warehouse in city B that has 5 sofas, and you have a furniture store in city C that needs to sell 5 sofas. And the point here is that the primal problem is sort of couched in terms of this idea that you own the resource the whole time that the network is operating, which is obviously you own the furniture store, you own the warehouse. And the goal of the problem is to find a way of keeping your corporate logistics balanced. That is, you need to make sure that if you're going to sell sofas at your store, you can get them to the store cheaply. But the model of the problem assumes that you're in complete control of the resource the whole time that the network problem is in play. That your goal is to find a way of equalizing resources across your corporation and spending the least amount of money doing so. So you want to equalize supply and demand to move the resource from your generation facility to where it's used. And that you're in charge of corporate logistics in that sense, whether it be sending power along power lines or sending trucks with sofas in them or whatever. We can find an interpretation for the dual problem that is similar but very distinct. And it instead refers to this idea of, instead of saying, how do I send the resource between cities? The question instead is, suppose I'm in a particular city. How much would be a fair price for 1 unit of the resource, taking into account supply and demand and shipping cost? So an example would be, for example, if I'm sitting at vertex C and I say, I've got 1 unit of my resource, and although we can still think about it as sofas or oil or water, for this part of it, let's think about the resource as electricity, because I think the interpretation will land a lot better if we do that. So I'm going to consider the flow in the network to be electricity. So there's a power plant in vertex B, and there is a high demand for electricity in vertex C. There could be a power plant in vertex C or vertex A, but for whatever reason, there is no excess capacity in vertex A. If there's a power plant in vertex A, all of the power is being used internally inside of city A. Similarly, the power plant in vertex B could make 10,000 units of power, but there are 5 left over. And vertex C, even if it has internal generation capacity, needs 5 units of power. So the question is, what is a fair price? Considering an open competitive market, what is a fair price for 1 unit of flow at vertex C? Well, here's what I would argue. First, if I'm standing at vertex C and I want 1 unit of flow, and clearly there are people that want flow at vertex C, there is a demand for it, so it's in shortage. If I need 1 unit of flow, 1 unit of electricity at vertex C, I could always have it sent to me from vertex B for a cost of maybe 9, maybe 7. So for that reason, I wouldn't, if I was a buyer in vertex C, I would never pay more than $7 for 1 unit of electricity, because I know I could always just get it by shipping it in for $7 from vertex B. But on the other hand, if I'm a seller, I don't want to charge $2, because if I'm a seller, where am I getting the power from in vertex C? If I'm shipping power in from vertex B, I'm paying $7. And so we can actually figure out what is a fair price. And it turns out a fair price is related to the total cost of shipping it in. And we also might observe that the dual variables y, v seem to correspond to these prices. We know already that y sub v corresponds to the cost of shipping a unit of flow through the spanning tree to a particular vertex. And actually, I should be clear about that. We think about the value of yv as sort of like the cost of going from the root to vertex v. But more generally, if I have a vertex u, the cost of going from vertex u to vertex v is just a differential of the two y variables. It's yv minus yu. So basically, I ship it up to the root first, and then I ship it back down using the spanning tree. And the reason that there's a negative there is because the value of yu is the cost of shipping it from the root to u. The cost of shipping from u to the root would be the negation of yu. And so we know that as we progress through the simplex method, the basis keeps changing because we want to find a more and more efficient supply chain. We want our spanning tree to be the lowest cost possible set of routes. And so it's true that shipping using the spanning tree might not always be the most efficient. For example, if this is my spanning tree, and I ship something to vertex C, it's going to cost 9 units. The fair price of 1 unit of flow at vertex C is 7 because I can get it in with only paying 7. But the reason is because this is not the optimal basis. In an optimal basis, it turns out my dual optimization variable yc will tell me what a fair price for 1 unit of flow at vertex C is. And it's very important for this interpretation that we only think about 1 unit of flow at a time. If I want to sell 10,000 units of flow in vertex C, that's going to be more complicated. It can't be modeled by this because I don't know about what I do with the other units. C only seems to have a demand of 5. There are only buyers for 5 units of flow. So I should only let's just talk about selling 1 unit of flow. So if there's any demand, I know there will be a buyer for it. And if there's any supply, I know there will be a seller. So the question is, if I have 1 unit of flow, and again, let's think about electricity, to sell in city C, what would be a fair price? The reason I want to use electricity is because this model, this fair pricing idea, requires us to use this qualifier. Not if you want to sell, if you're in the market to sell. No. If you have to sell, you have the flow, you are required to get rid of it right now. You have no way of getting rid of it besides exchange on the open market, besides selling it. You are required to sell it. You have to set a price that a buyer will take under every circumstance. Even if that means setting a terrible price, you are required to sell 1 unit of flow. Now in city C, if you wanted to sell 1 unit of flow, you could expect to make money. You could expect to set a positive price for it because there are buyers. There is a demand in the city, which means that there are buyers that would buy at least 5 units of flow. And so just to be clear, the way that we're doing this, the question that I've just asked is you have 1 unit of flow and you must set a price so that somebody will buy it. You have to set whatever price a buyer would pay. So obviously, if you're sitting at city C, you could set whatever price you wanted. I could say, I'm going to charge $10,000 for a unit of flow. The problem is, if you set a price that's higher than the price of transporting flow in from vertex B, which is $7, then a competitor will come in and charge, if you charge $10,000, they'll charge $10. They will come in and undercut you, and you will not get any business. You won't make the sale. You have to set a price so that a buyer will actually pay it, and a competitor can't come in and outprice you. On the other hand, it doesn't make any sense to charge less than the cost of shipping the flow in. If you're at vertex C and there is a net demand, then where are you getting this 1 unit of flow from? You're probably shipping it in from vertex B, where there's an oversupply, because we know that the total amount of flow in the network sums to 0. So there is no way that you have a unit of flow that isn't accounted for by these supplies and demands. So if you're in vertex C, you know that it costs $7 at least to get a unit of flow. If you're going to sell that unit of flow in vertex C and you sell it for $5, you're taking a loss, which doesn't make sense because there are buyers, and no buyer in vertex C can get a unit of flow for less than $7. So it makes sense that the fair price, the price on an open competitive market, would be $7 for 1 unit of flow at vertex C, which happens to be exactly the minimum price of shipping flow in from elsewhere. Now, just to be clear, I know it's weird to say, well, why would you sell it for $7 if you're just breaking even? Keep in mind, we can think of this sort of like a wholesale price. Obviously, if you're selling it in retail, you put a markup on it, but all of your competitors put the same markup on it. So the markup is sort of independent of the price of actually obtaining the flow. So think about this like the wholesale price. What is a fair price for 1 unit of flow at vertex C? It would be $7. I mean, you could ship it the expensive way, but that wouldn't be profitable. It would always be cheaper because we can send as much flow as we want. It would always be cheaper to ship it via City A, so it would be $7. So the fair price at vertex C for 1 unit of flow, because there is a demand, so there are buyers, there are people willing to pay for flow, a fair price is $7. And so maybe it's clear what I'm doing here. What's going to happen is, in general, in a city that has a demand, where there are buyers, the fair price will equal the minimum cost of shipping that resource in from elsewhere. So in this case, that would be, in such a simple example, it would be the price of shipping it in from vertex B via this route. What about this question, though? So I want to talk about the fair prices in every city. If I have to sell 1 unit of flow and I'm in city B, what's a fair price? So this is a strange one, and it starts out counterintuitive. I sort of mulled this over for a while, but eventually a light bulb sort of turned on. And as I said earlier, I believe this interpretation, a few graphs I'm going to show, these little triangular graphs, I think this captures all of the significance of the course. This one sequence, the next 10 slides, I think encapsulate all of this entire course, all of the profound interpretations of LPs, of the profound things we've seen involving duality, all of them get summed up in this set of examples. So the question is, you're at City B. In City B, there is an oversupply. What I mean by that is, if we account for all internal supply and demand, there are still 5 units left over, which means that there's nobody that wants to buy a unit of flow. Because if they wanted to buy a unit of flow, there'd be more demand. But there isn't demand. There's an oversupply. So if you're selling sofas, there are a bunch of sofas sitting out on the sidewalk. Nobody wants them. But suppose you're selling electricity, and that means that you have to sell 1 unit of flow. And the reason I keep saying that we should think about electricity is that the next little bit of this interpretation seems counterintuitive, but I can prove to you that it's intuitive in the context of real-world electricity pricing. So suppose you're in City B, and you are required to sell 1 unit, or in this case 5 units, but suppose we're just working with 1 unit, you are required to sell 1 unit of electricity in City B. What is a fair price? You have to set whatever price that a buyer would pay, even if that means a bad price. So the fact that City B has an oversupply means that nobody in town is interested in buying, because if they were, they would have already bought it. On the other hand, it is true that in City B, a unit of flow has value, because if you have 1 unit of flow from City B, you could walk over to City C and sell it for $7. The problem is, it would cost you $7 to do that. To go from City B to City C, to take your 1 unit of flow from City B to City C, it would cost you $7. Okay, so I'm in City B and I have to unload 1 unit of flow. What do I do? How do I attract a buyer? Well, I guess I could pay them. Nobody wants the flow in City B. But if I pay you $7 or $8 or $20, doesn't it suddenly become profitable to take the unit of flow? Yeah, I guess it does. If I pay you money, then that would cancel out the cost of having to ship the flow elsewhere. So if I am required to dispose of 1 unit of flow in City B, if I have no other choice, what I could do is I could set the cost to be negative. I could pay somebody to take it off of my hands. If I do that, suddenly it would become viable to ship it elsewhere to sell it. And that would mean that I would suddenly have a buyer. In an open and competitive market, somebody would want to take it off of my hands if I pay the right price. And the fair price would be negative $7. Which way do I write that? Dollars. Oh, that's even worse. Okay, so we'll write it like this. Negative $7. The price of flow at vertex B is negative $7, which still feels weird. Why would I sell it if I'm not going to make a profit? Why would I have to pay somebody to take it off of my hands? The key thing is I am required to dispose of it. I have nowhere to store it. I have to get rid of it. Even if it's a sofa, even throwing it in the garbage costs something. I have to get rid of my sofa, and I have to pay somebody to haul it away, right? I'm required to dispose of this resource. There are places in the world where there is a chronic shortage of sofas where my sofa would cost $100. But I need to get rid of my sofa in a city full of extra sofas. That means I have to pay somebody to get rid of it. So one way of viewing this fair pricing is, well, maybe your resource is not desirable in certain contexts. Maybe City B is full of extra sofas. The way I want to conceptualize this is electricity pricing. So you may know a little bit about electricity generation. I don't know that much, but When you generate electricity, you have to have some sink for the electricity. You have some way of actually using the power that you generate. Because if you don't, the electricity grid can be destroyed. It can actually be damaged. If you're generating more electricity than you're actually using, then the grid can actually become compromised. That means, of course, that power generation across an electricity grid has to be balanced with demand. And that also means that there are lots of places in the world where, due to peculiar local phenomenon, they have to prepare to increase electricity generation at certain times of day and decrease it at others. Very famously, there are stories, there's like an old documentary about how in Britain, they often would bring on extra power generation or import power from Europe at specific times, at commercial breaks during popular TV shows, so that because they know that during the commercial break, everyone's going in their kitchen and plugging in the tea kettle. And they need to make sure there's enough power supply to meet demand at those times, but they also have to shut the supply down at the end of the commercial break because it would damage the power grid to have more electricity being generated than is being used. That's all fair enough. They can always balance supply and demand by bringing capacity online and taking it offline. But there are also cases in electricity generation networks where so much power is being generated by what you might call passive sources that they actually have to begin paying people to use electricity. A common case of this, I actually went looking for a news article so I could put a screenshot of it in my slides. And what I discovered was this happens so often these days that it's no longer a news event. I could find articles from like 10 years ago about this. But it happens so often that I couldn't find articles from like this year. For example, in California, which now has a huge amount of solar generation, a large number of solar power generation projects, on really bright days, so much power gets generated that the wholesale price of electricity goes negative. That is to say, the power company has to pay people to use electricity. There are actually places in the world where even consumers, even retail electricity, somebody sitting at home actually has the cost of their electricity go negative at certain times of day. The power company pays them to turn on their heat or to turn on their air conditioning to use up electricity to balance with the immense amount of supply. It's not just from solar generation, but it's often caused by the use of renewable electricity sources like solar and wind, because we can't necessarily account for the fact that when on a really bright day, we're going to get a huge amount of sunlight that's going to create a huge amount of electricity. With fossil fuels or something, we can plan ahead and say, we'll just burn less coal or whatever if we don't expect much demand. But one of the interesting consequences of renewables is they've become so effective that we end up with situations where we have more power than we know what to do with. And we end up in exactly this case. I'm sitting on Vertex B, I'm generating way too much electricity. I need to get rid of all of it. I need to do whatever I can to use up that electricity, even if that means setting the price to be negative. And this actually happens. It's happening right now. As I record this lecture on a morning on July 11th, there are places in North America where people are being paid to use electricity, mostly industrial consumers. There are probably places in Europe where people are being paid to use electricity, even people in their homes, because too much is being generated, not just because of renewables, but probably including because of renewables. And so this is happening right now, and it's happening as you watch this video. So it's valid to talk about cases where setting a fair price involves the price being positive in some places, because far away from my power generation station, it still costs money to use electricity. But here, I have to pay somebody to take the power off of my hands. So I think this is a reasonable interpretation, that a fair price can indeed be negative, even for some concrete commodity like electricity. So what is the dual problem actually saying? So if I think of these the dual optimization variables in the optimal dual solution as being the fair price for my flow at vertex, in this case vertex C or vertex B, what do I make of this dual objective function, which is a strange linear combination of these fair prices? Well, if we look at the dual objective function, we'll notice that, so in vertex B, I had a total supply of 5, but yet in the dual objective function, the coefficient is negative. And the reason it's negative actually goes back to part 2 or part 1. In part 1, I said something like, when we derived the constraints, these two big sums the two sums to derive the balance constraints, we started with this form here, and I said, executive decision. I'm deciding to negate both sides of this. I'm allowed to do that. I know it's weird, but it'll make our life easier later. The reason that that made our life easier was that it meant that when I took the transpose of this matrix and I ended up with my dual variables, YC ends up being the cost of transporting flow from the root to vertex C. If I hadn't negated both sides, it would be the cost of transporting flow from vertex C up to the root, which is a bit less intuitive. And it also makes it a lot harder, I think, to conceptualize how to compute the dual optimization variables. So the reason I negated both sides was to make it easier to derive that computation for the dual optimization variables. On the other hand, by negating both sides, I put a negative sign over here, which when I took the dual, put a negative sign in the dual objective function. So now the chickens have come home to roost. So what is my dual objective function? Each term in the dual objective function is the total demand at that vertex, because it's the negation of supply, multiplied by the fair price at that vertex. And what this ends up equaling out, so once I take this complete linear combination, what I'm really doing is computing the same thing in the optimal case as the primal objective function, which is the total cost of balancing supply and demand. I'm just not viewing it the same way. In the primal function, I balance supply and demand by sending flow around the network. In the dual function, the balance I'm looking for is if I sell all of the flow in every vertex, including vertices with a supply and vertices with a demand, if I sell a certain amount of flow, the amount that corresponds to the demand in that vertex, at every vertex, how much money do I have when I'm done? So I sell this amount at the fair price at that vertex. That can be interpreted as a way of viewing the objective function. And therefore, the objective itself is to maximize the overall revenue from selling all units of flow that are in demand at each particular vertex. Keeping in mind that results in me having to do something weird like selling -5 units of flow at a vertex with excess supply, which is a bit of an odd way of parsing it. But I'd say that if we have that interpretation of the Y's as being fair prices, we can appreciate that maybe the modeling for how we have to dispose of all of our supply might be a little bit odd looking. But maybe the key thing to accept is that each Y variable represents the fair price of flow at that vertex. So the next question I guess we should ask is, when is the dual going to be unbounded? We had a hint earlier with the pivoting how to detect it, but what does it mean when the dual is unbounded? So we know already that the global supply and demands have to sum to zero. And the reason why that's significant, of course, is that means that these coefficients are never going to be infinite. What I'm asking is, when is the dual going to be unbounded? When is this going to go to infinity? Well, it's going to go to infinity either if the coefficients go to infinity or if the Y variables go to infinity. But because supply and demand have to sum to zero, I think it's a reasonable conclusion that these coefficients can't be infinite. Okay, so fair enough. And also infinity is not a number, so lots of reasons. So for the dual to be unbounded, obviously one or more of my Y variables has to become, I'm going to say unbounded, because it turns out, as you may notice because of the negative sign, a Y variable going to negative infinity could result in this maximization problem going to positive infinity. And if I stare at this, I might realize what's really going on. The dual problem is unbounded only if I can make this go to positive infinity. There's no reason a maximization problem would ever want to go to negative infinity. So when can this go to positive infinity? Well, the obvious case is if this goes to positive infinity, then the whole thing goes to positive infinity. But if this here goes to negative infinity, so if Y sub b goes to negative infinity, then the negative sign means the dual is unbounded. Well, notice that when this actually happens, it turns out both will go to infinity in a different direction. This goes to negative, this goes to positive at the same time. So how do we interpret that? Okay, the dual is going to be unbounded if the Y variable can be made arbitrarily large at a vertex with net demand. Remember that the coefficient is the total demand at the vertex. If the vertex has demand and we can make the Y variable large, in other words, if the fair price at a vertex with demand goes to infinity, then my overall revenue, of course, goes to infinity. On the other hand, In a vertex with excess supply, so a negative coefficient, if the fair price there goes to negative infinity, and this is seeming very abstract, how can the price be negative infinity? If the fair price goes to negative infinity, that also makes my dual unbounded. And as I said a minute ago, it turns out we'll see these are actually paired up. If the fair price at one vertex goes to negative infinity, due to the global balance of supply and demand, there will be another vertex where the fair price goes to positive infinity. And those are the circumstances, the intuitive, I guess, the interpretation of when the dual is unbounded. I don't know if we should use the word intuitive just yet. Can I justify this? So, under what circumstances could the price become arbitrarily large? What does that even mean? I mean, we know that there is a global balance of supply and demand. So if there's a vertex with a total demand, so here's vertex V, it's got a demand of -5, I know that somewhere in the graph there is supply to make up for this. So how could the cost become infinite? Like, maybe it's just really expensive, but I should be able to get the flow to vertex V. One way to think about this is, what does it mean for the problem to be primally infeasible? Because we know there is a sort of relationship between dual unboundedness and primal infeasibility. That's one thing to keep in the back of our heads. So if a vertex has net demand, in other words, if the supply is less than 0, then there are buyers for the resource at vertex V. Somebody does want to buy the flow at vertex V. It makes sense, therefore, that I could set a price that was positive. If I were selling, I'd be able to actually make money. Somebody would pay me for flow. We also know that, as I said a minute ago, there is going to be flow somewhere that makes up for the demand at vertex V. So what does it mean for YV to become arbitrarily large? Well, what that means is apparently that the fair price of flow at vertex V becomes infinite. In other words, the cost of shipping in flow from some other vertex has to be infinite. So when is this going to happen? Well, we know there is enough flow to satisfy demand. So why would it become impossible to ship in the flow? Well, the only reason is, I guess, if I simply can't bring it in. The flow might be somewhere else in the network, but for whatever reason, vertex V, here's vertex W, I just can't reach vertex V from vertex W. There is no way of sending flow to vertex V. Even though the flow exists, there's no way of meeting that demand. Under those circumstances, if there are buyers in vertex V that want flow and they'll pay whatever fair price exists, if there's no way to get the flow, the price will become infinite. Let's consider this. So here we have a modified version of our graph from earlier. There are buyers at vertex C. They will pay a fair price. They will pay whatever it costs to get the flow into vertex C. But I can't. There's a supply at vertex B. We know that our network is weakly connected because we assumed that it would have to be. There's a supply at vertex B, but there's no way to get that supply to vertex C. And therefore, at vertex C, where there'll never be any flow, because there's no way to bring flow in from elsewhere, the price will be infinite, because there's no amount of money you could pay that would ever get you 1 unit of flow in vertex C. And we might stare at this and realize, wait a minute, this is primally infeasible. There is no way to send flow from vertex B to C that's primally feasible. This corresponds exactly to primal infeasibility. This dual is unbounded because the price of flow at vertex C is infinity, because there's no way to ever get flow, but there are buyers for it. And it happens to correspond identically to the case where we have primal infeasibility, which makes some sense. We know from duality we should expect that connection. And so I really like this. I spent a long time mulling over this economic interpretation. When I drew it out like this, I was really struck by this. This is one more piece of evidence. These two interpretations, fair pricing and logistics, moving flow around, they're brought together by duality, but duality also everything locks in if we consider all of the extreme cases. Dual unboundedness does equal primal infeasibility, just like we expect it to. Now also consider in this graph what happens at vertex B. So in vertex B, I've got 5 units of flow, and I have to get rid of them. I will do anything to get rid of them. I'll pay somebody to take those units of flow off of my hands. How much do I have to pay them? Well, nobody will ever buy the flow from me, even for a negative price, unless they can get rid of it too, because everybody has to find a way of getting the excess supply to actual buyers, to people that actually demand the flow. So somebody in vertex B that wants to buy flow from me has to have some way of getting rid of it. But they don't. There's no way to get the flow to vertex C, which is the only place that there are real demands for it. That means that there is no amount of money I could pay somebody at vertex B for them to take the flow off my hands. In other words, the price of flow is negative infinity. There is simply no price I could set, even negative, that somebody would pay to take the flow off of my hands. And so so in this case, the dual is unbounded for two different reasons. It's positive infinity, the price is positive infinity up here, and negative infinity down here. And because we know that supply is globally balanced, if we have a vertex with positive infinity as its price, there has to be another vertex with negative infinity. This vertex here will never have a positive or negative price. The price is just going to be zero, because at this vertex there are no buyers and there are no sellers. You could argue there's no way to obtain flow here, nor is there any reason I would want to. I can get flow from vertex B, but I wouldn't want to. There's no demand, and there's no way of sending it on elsewhere. Just to be clear, though, here is a graph that is also dual unbounded. Vertex C has a demand, and there's a way of satisfying a little bit of that demand. I can send 2 units up this way, but once I do that, there's still a demand, and there's no way to satisfy the remaining demand. And so the graph is still dual unbounded in this case. It's true that I could do a bit more pivoting or something. I could get a little bit further into a solution before I got into trouble, but ultimately I'd still reach a case where the fair price at a vertex becomes infinite. And similarly, the fair price at some other vertex goes to negative infinity, and the dual becomes unbounded. Okay, one more thing. This is the observation. I consider this final little bit here, which is a way of revisiting the previous lecture. I consider this to be the final piece in the puzzle for this course conceptually. We've got one more thing to cover after this slide and the next one, those two-phase methods. But I think the conceptual and theoretical peak of this course, the crescendo we're building to, is here. So let's think about this example here. This is a case that is primally unbounded. So notice that if I'm standing at vertex A, and I have my unit of flow, I could send it to vertex B, it would cost me 1, send it to vertex C, so now a total cost of 3, and I send it back down to vertex A, and I make a profit. I actually get $2 every time I send a unit of flow all the way around the cycle. So the question is, what are some fair prices for flow at each of these vertices? I'm standing at vertex A, and my goal was to set a price that I would sell the flow to somebody such that I make as much money as possible. That's why I can't overprice it because then nobody would buy from me. I don't want to underprice it because then I wouldn't make money. I want to set a fair price that makes me the most money. So how do I make money? Well, if I sell flow at vertex A, I'm going to pay a negative amount because obviously there's an oversupply at vertex A. If I sell flow at vertex C, I suppose I could make money if I sold it there. The question is, what would make me the most money? How much should I charge? Well, let's think about this. How do I set a fair price? If I sell the flow for $10, the buyer of the flow would take it and send it around in a circle forever, and they just make as much money as they wanted. But I only ever make $10. If I sell the flow, I only make the amount that I sell it for. Suppose that I don't sell the flow. Suppose I'm standing at vertex A, and I have a unit of flow, and I refuse to sell. I say, I'm never selling this. I'm going to hold this flow permanently. Instead of selling it, I'm going to send it around I'm going to send it around this triangle once. I'm going to make $2. I'm going to send it around. I wish I could draw triangles. I could send it around again, make $2 more. Send it around again, make $2 more. I am never going to sell. I'm just going to keep my unit of flow. I'm going to hold it. I'm going to send it around this cycle forever, for all eternity. And I'm going to make infinite profit. It doesn't make sense if I can make infinite profit by holding the resource to ever sell it, because no finite amount that I could sell it for would ever make me as much money as not selling. If I set a price, any price, I am losing money. And therefore, it's a contradiction. If my goal is to set a fair price that makes me the most money, then the best option, this is an example of a game where the best strategy is not to play. If I simply refuse to set a price, I will make infinite profit. And so in this case, we know already that the primal problem is unbounded. The minimum cost is negative infinity because I can just run the same unit of flow around the cycle over and over again. So we know the primal is unbounded. We expect the dual to be infeasible when the primal is unbounded. But why is the dual infeasible? The reason is because the goal of the dual is to set fair prices for the cost of flow. And in this example, because of the weird situation where I make an infinite profit by holding the flow instead of selling it, it doesn't make sense to define a selling price at all. There is no such thing as a fair price. There do not exist a set of y values that are feasible for my dual problem, because the best option is to hold the flow and to never buy or sell. And as a result, it makes sense, the dual problem of finding those fair prices, that is infeasible. So we have been able to take this minimum cost network flow problem, convert it to an LP, find an interpretation of those variables in the LP and the dual variables. We understand the interpretation of what the primal LP means. Over the past 20 slides or so, we have found an interpretation of the dual LP, and although there were some parts of it that were a bit strange, like the idea of costs going negative, I think I was able to pull us through that. I think we can understand why in an actual practical example, there are cases where a resource's price can go negative because you have to get rid of it. And not only that, we were able to take that interpretation and tie it back in using duality even to the extreme cases. We were able to see why reasonably prices can become infinite in places where there is a demand but there is no way of satisfying it. We were also even able to parse this strange situation where we can't set fair prices at all because the best option is not to sell. There is no market for buying and selling because everybody is better off if they simply run the flow around the cycle for all eternity. So I think that that is a great way of tying together all of the different loose ends that we've seen over this course as far as the conceptual or, I don't know, philosophical meaning of linear programs is concerned. But we're not done. We've still got to deal with a bit of an epilogue, which is, well, wait a minute. So we know about finding unboundedness in the dual conceptually, so let's just make sure we know how to do that in practice. And then finally, in the practical sense, we've reached the theoretical, philosophical peak of the course. We have a couple of other things to do, I guess, as a nice cool down lap, which is we want to actually solve some more linear programs. So we know that unboundedness occurs whenever we have a situation where we cannot fully satisfy demand at some vertex, which will drive the cost of flow at that vertex to infinity. And of course, that corresponds to primal infeasibility. The question is, how do we detect that? And the answer is basically we're going to end up with a situation. If I'm sending flow, I knew I was going to need this diagram again. If I'm sending flow between components and I do a bunch of dual pivots, suppose there is a situation where demand simply can't be satisfied. Well, I'm never going to reach an optimal solution if demand can't be satisfied. So at some point during one of my dual pivots, I will have a situation like this. I'm sending -3 units from C0 to C1, which of course means I'm supposed to send 3 units from C1 to C0. So C0 overall has a total demand of 3. And so I go looking for a way of sending 3 units backwards. But what if I discover that there are no arcs pointing from C1 to C0? In this case, I know that my entering arc has to point from C1 to C0. If no such arc exists, that means that I need 3 units of flow over here and I'm never going to get them. So the price of flow in C0 will now go to infinity because there is a demand that cannot be satisfied. And so I will be able to discover unboundedness by basically discovering that primal infeasibility case during a dual pivot. And so I think if we just go through an example, this description, I think, says everything I just said. So this is the same example graph we've been using all along with one modification, which is that the usual example has the arc FE. I have replaced this with the arc EF. And so now we have this situation happening, which is if I look at everything that's above this sort of cut in the graph here, and I add up the total supply, I've got 10 units plus 1 unit is 11, minus 6 is 5, minus 2 is 3 units. So there is an oversupply of 3. And that means that I can assume that there is an undersupply of 3 down here. And if we just stare at the graph, we realize that there is no way of getting flow from up here down to the lower component. And therefore, we should expect the dual is going to be unbounded. There is going to be a need down here for 3 units of flow that will never come. And as a result, the price of flow down here will go to infinity and the dual will become unbounded. So let's try doing some dual pivots. So here is a dual feasible basis. Let's do some pivots. Okay, so the first thing with the largest coefficient rule, we're going to go through just, it'll be good practice. We'll go through a few pivots. So our leaving arc is HG, and then we predictably are probably going to add that. Yep, there it is. Good. Okay, we take a look again. Our total cost is 138 for all that's worth. Now our leaving arc is going to be EF. Because of the -8, and we're sort of wondering whether maybe this is going to be the place we discover unboundedness. But remember that the unboundedness is between these two halves of the graph, and we actually haven't separated them yet. So if we remove that leaving arc, our component C1 will be this thing. And so we're going to choose an arc in an opposite direction. And so our current leaving arc points into C1. So I guess we're going to pick Fi as the entering arc. Yep, there it is. Okay, so we assign the flow. Okay, so now, just because of the quirks of the largest coefficient rule, we go down and begin doing some housekeeping in the lower component. Okay, so we're going to choose the arc AE, and we're going to swap that predictably. So C0 is just A here. So we're going to swap that for the arc, I presume, BA. Yep, there it is. Okay, finally, we end up here. So our leaving arc is DI, and that means that this is our component C0. And we go looking for an arc that points in the reverse direction, into C0, and we don't find one. There isn't such a thing, it doesn't exist, and that means there is no way to convey the 3 units of flow that are supposed to go from vertex I to vertex D. There is no way to convey those to vertex D in a feasible way. And as a result, there are no candidates for my entering arc, and so the price of sending flow from vertex I to vertex D, either directly or indirectly through a bunch of other edges, that price now goes infinite, and therefore the dual is unbounded. And so we can detect dual unboundedness, I think, in a very nice, dual way to the way we detect primal unboundedness. While we're doing our pivot, we divide the edges by their direction, and if we discover that there are no edges in the direction that we want, then we've found unboundedness. Okay, so finally, the very last thing we have to cover in this course is if I hand you an arbitrary network flow problem. So I say, here is a graph that has a supply value on each vertex, and it has a cost value on each edge, and that is literally all that I give you. If I supply you only those 2 pieces of information, can you now give me an optimal flow? Or at least tell me that there isn't such a thing. So we call that solving the problem. Just like with an LP, it is valid to say the solution is that the LP is unbounded or completely infeasible. So what do? Well, the first problem is, in all of the examples we've seen so far, I've handed you something and said something like, oh, well, this is a feasible basis, now do some pivots. So the problem here is that I didn't even give you any basis, much less a feasible one. So I need to come up with a basis. Frankly, I'll even take an infeasible basis, just for the sake of having something to work with. So the first question is, given a network, how do I come up with any basis, a valid basis, even if it is an infeasible, both primal and dual infeasible? And the answer is, I could use a graph traversal algorithm to compute an arbitrary spanning tree. So I treat the graph as if it's undirected, and I perform depth first search or breadth first search. So I could do that here. So let's do depth first search. So A to G, G to H, H to I to J, go around here. I think I might even be able to get a nice spiral looking one. All right, there's a spanning tree. This is a basis. It's probably not going to be a very useful basis. It probably will be infeasible, both primal and dual, but I can use a graph traversal algorithm to find some initial basis to work with. Now, the slides are probably going to suggest, they don't suggest the same one, but the key thing is, starting from nothing, you can just run a graph traversal algorithm, either on paper or with a machine or whatever, to compute some basis to work with, some spanning tree. Now, this basis is neither primal nor dual feasible. We can see that there are primal infeasible arcs and dual infeasible arcs. But we have something. You've got some spanning tree to work with. So now the question is, what do? I can't run either the primal or dual simplex method because I need to have either primal feasibility or dual feasibility to do that. So what we'll do is the same thing that we did with regular linear programs, with general LPs, which is we'll find a way of starting from basically nothing and then modify the problem just a little bit and use that modified problem to find a feasible basis for the original problem. And this is essentially the initialization phase of the regular simplex method, where we would normally, for example, solve an auxiliary problem or use a two-phase method. And my goal today is only to talk about the two-phase methods. We're not going to try and come up with some network analog of the auxiliary problem. I mean, we can, I just don't want to do that. And I think you might agree that adding in that variable omega would require us to understand its interpretation, which we really don't want to do right now. That is something we can get around because these two-phase methods, which we've seen before in the context of duality and the linear algebraic simplex method, we hopefully believe in them enough by now to trust them, and I think that they will work better. So what is that two-phase method I keep talking about? Okay, so let's think back to the slides on duality or from the linear algebraic simplex method and consider an LP like this. So if I construct the initial dictionary for this LP, and I want to be clear, this LP is actually feasible. It's just not initially feasible if I make it into a dictionary, and we can see that here. There are feasible points, we just don't know what they are. So if I construct the initial dictionary for the LP on the left, it is not going to be initially feasible either for the primal or the dual. The dual dictionary won't be feasible, nor will the primal one, so what do I do? Well, one option would be to think about, like we did before, what about this LP? So it's the same LP, except that I've set every objective coefficient to 0. That's it. Everything else is the same. And you would agree with me that any feasible solution, whether it's optimal or not, any feasible solution to this LP has to satisfy all of these constraints, which means it has to be feasible for this LP too. So if I can find a feasible solution to the LP over here, I will have a feasible solution that I could use to start running the simplex method on the LP on the left. Okay, so what's the point then? Like, how are we not back at square one? Well, one thing is, by changing all of the objective coefficients to 0, the LP is now dual feasible. If I construct a dual dictionary for this, I will notice that it is dual feasible. In fact, it'll be degenerate initially, but it will be feasible. So what I could do is I could construct the dictionary for this modified LP, and it'll be dual feasible, but not primal feasible. I could run the dual simplex method on it, which will get me to an optimal solution for this LP here. An optimal solution has to be both primal feasible and dual feasible. So the optimal solution to the LP on the right has to also satisfy all of the constraints that I have in my constraint system, of course. And therefore, I could compute the optimal solution to the LP on the right. I could bring it back over and use it as an initial primally feasible solution to the LP on the left. And I could then solve that LP with the primal simplex method. So it's a two-phase method because I use the dual simplex method on the modified problem, and then I use the primal simplex method to bring it home. I start from that feasible basis, and I get to the optimal solution. This is what I just said. And so this is an example of one of those two-phase methods. The reason I think these are nicer than the auxiliary problem is all they require is for us to know about both primal and dual pivoting. They don't require us to build a second LP with omega and then interpret that and pivot omega out of the basis or whatever. Now, if we were to discover, if while solving this, I were to discover that that this modified LP is unbounded, and for a lot of reasons I don't expect that to be the case here, so one of the reasons is because the objective function is obviously 0, then I wouldn't have any primal feasible solution at all. Now, another thing to observe about two-phase methods is that because of what we know about duality, a two-phase method will there's no reason that the dual going first is necessary. I could have the primal LP go first too. And so what I could do is I could modify the LP to make it primally feasible but not dual feasible. So that would be setting basically the right-hand side of every constraint to 0. When I do that, I would end up in a situation where when I solve this, I could then perform primal pivots on this modified LP. And if I solve it, I would then be able to, I would have a solution that is both primal and dual feasible for this modified LP, which would have to be dual feasible for this LP. So I could then use the primal method to solve the first phase, the initial problem, and the dual network simplex method, dual regular simplex method to solve the original LP, starting from the basis produced by the optimal solution for the one on the right. So I could do a primal first two-phase method as well. It doesn't have to be dual first. In general, when I say two-phase method, therefore, I'm referring to one in which I'm using both primal and dual pivoting, not necessarily in any particular order. There isn't really a general advantage to starting with the dual or starting with the primal. So we can apply the same logic to derive a two-phase method for network problems. Now, the thing I'm going to not go into much detail about this semester, just in the interest, because we're already running 2 hours on this lecture, is I'm not going to talk as much about the way we would structure our first phase to properly detect unboundedness. Instead, I want to focus on simply doing the two phases. It turns out that by using a different objective vector, I can better detect unboundedness or infeasibility. For the time being, I'm instead going to focus on simply going through like the overarching arc of these two-phase methods. So here's the idea. I have some arbitrary basis. And my goal is going to be to find some way of turning this into a primally feasible basis, even if it's not optimal, so that way I could then run the primal network simplex method to get an optimal basis. Or alternatively, turning this into a dual feasible basis so that I could run the dual network simplex method. What I'll do is design a two-phase method. So I'll observe that the reason that a basis is primally infeasible is because the set of supplies and demands can't be balanced out by feasible flows using the basic edges. So that is to say, this is infeasible. This -4 is here because I need to send 4 units of flow from A to B. If I didn't have to do that, this wouldn't be -4. If, for example, I didn't have to send any flow from A to B, there wouldn't be a negative number here. There would just be a 0. So I notice I could make any basis primally feasible if I just pretend that every vertex has a demand of 0. So I set the entire supply of the graph to be 0. In that case, all of the flows across edges would also be 0, and therefore I'm guaranteed to have a primally feasible basis. On the other hand, a basis is dual infeasible if there exist cost differentials that would allow me to have a lower cost basis. That is to say, what this is telling me, this dual infeasible edge, this is telling me that if I add this edge to my basis, I'll save money. So the question is there a way I could force any basis to be dual feasible? And one way of doing that would be to make sure there are never any cost differentials. So I could set the cost of every arc to be 0. I could also set it for better detection of things like unboundedness. I could set it to 1 or something, which would allow there to be at least some intuitive modeling of cost. But if I set every cost to 0, then what I'm going to end up with is a case where it's impossible for a dual slack value to ever equal anything other than 0. And this is evident in a few different ways. One of them is if you consider the way that the dual optimization and dual slack variables are actually computed, which is something like this. You might observe that if the cost is always 0, and we recursively compute the y variables from the root on down, and the root's value is 0, these are all just going to go to 0. Everything will always be 0. And therefore, if all costs are 0, every basis is going to be dual feasible. This is now just going to say what I just said. So a basis is primal feasible if we have no negative flow, and we can make sure that there are no flows at all if we set every supply to be 0. And therefore, we can make any basis feasible, primally feasible, by just setting all supplies to 0. Obviously, that changes the problem, but our goal is to find a way of making progress. Now, the same thing is true about dual feasibility. If we set every cost to equal 0, then we're guaranteed to have any basis be dual feasible because no cost differentials can exist. So I think about that and I realize what I could also observe is that if I set, maybe I'll use this as a point of comparison. If I were to set all supply values to 0, that would mean all of my primal flows go to 0. But would it change anything about the dual slack variables or the dual optimization variables? Well, no, because those are computed separately. They're based on cost. Therefore, I could perform a bunch of primal pivots on this now primally feasible basis to compute a basis that is optimal for this modified graph, which will be both dual feasible and primal feasible. Because dual feasibility depends only on the costs of edges and the choice of basis, any basis that is dual feasible for the modified graph will also be dual feasible for the initial graph. And that means I could use it as the beginning of the dual network simplex method once I'm done. That's the insight that I need to build my two-phase method. So here's the two-phase method that runs the dual network simplex method first. So you give me an arbitrary graph, and suppose that I can't find a basis easily that is primally or dual feasible. I'll do this. I'll make up a new graph G prime. That's a copy of my graph G with all of my edge costs set to 0. Okay, so I set all costs to 0. That means any basis will be dual feasible. So I compute an arbitrary basis. And because all costs are 0, all the dual slack values are going to be 0, and therefore the basis is feasible. I now apply the dual network simplex method to compute an optimal flow for G prime. I know that because I haven't modified any of the primal parameters, that is to say, the supply values for each vertex, that any primally feasible flow that I come up with will be primally feasible for the original graph. So I solve the problem to compute a flow that I know to be both primal and dual feasible for G prime. And then I know that that's primal feasible for G prime, and it will be primal feasible for my original graph G. So I take the basis that I was using in my last step to get this optimal solution, and I bring it back over to G. And I use that basis as the initial basis to run the primal network simplex method on G. Odds are that basis will not be dual feasible for G, but I can use the primal network simplex method to find a dual feasible basis, to find an optimal flow. Now, the primal first version is basically the same. I just do things in the opposite order. I construct a new graph G prime, and I set all supply values to be 0. That means all flow values will be 0, which means every basis is primal feasible. I then run the primal network simplex method to compute an optimal flow, and this optimal flow in my new graph G prime will be both primal and dual feasible for G prime. Because I haven't changed any of the conditions for dual feasibility, the resulting basis will also be dual feasible for my original graph. So I bring it back over, and then I run the dual network simplex method on my original graph to find the optimal flow. Now, I mentioned there are a couple of nuances to the way that unboundedness and infeasibility are detected in the middle. We're going to ease off of those. We would be able to detect them in one of the two phases of the algorithm. We're going to ease off a bit on that for the sake of this course, just because I want to make sure we get to the two-phase methods, even if we don't go into too much depth about that aspect. That's why I'm not spending as much time talking about that. Okay, so I want to go through two examples. I want to do one where we do the dual first, one where we do the primal first. I will also, like I did earlier in the course, post a bunch of extra auxiliary slides full of a bunch of other fully worked examples with each individual step so that you can practice the pivoting procedure and verify your answers. Okay, so starting from this completely infeasible basis, so it's neither primal nor dual feasible, let's use a two-phase method to solve this network flow problem. In this case, it dictates you must do the dual method first. So I'm going to set up this modified graph where I set all of my edge costs to 0. And I'm putting them in orange to indicate that they're definitely phony. Like, this is clearly not the actual cost of that edge. I'm just inventing that. That's a device I'm using as a way of moving towards a feasible basis. So as a result of setting those costs to 0, all of my dual slack variables are now 0, and I therefore have a dual feasible basis, and so I can do a bunch of dual pivots. So I'll do that. So I'll perform dual pivots until I get to an optimal solution for this modified graph. Okay, so at my first step, my leaving arc is BA. I think that separates us out this way. And in this case, you might notice there are going to be a whole bunch of ties for the entering arc. Let's move over and take a look. Oh, actually, not this time. Sorry. There's only one arc that enters the component C1, so it's EC. So we transfer the flow, and we go to the next iteration, and the total cost is 0. The total cost is probably going to be 0 for most of this. I now take a look at, there's CD, so CD is still primal and feasible. It is my next leaving arc. In this case, D just gets cut off from the rest of the graph, so I choose an arc in the opposite direction. Now, in the case of a tie like this, the slides are going to choose the to break the tie. They're going to essentially use a lexicographical ordering, or they're going to use sort of the equivalent of Bland's rule, which is DF F comes alphabetically before J, basically. So it'll differentiate that way. It'll therefore choose DF. Either would be a suitable choice. Obviously, a pivot selection rule would still, unless it was randomized, be deterministic. Okay, so I do this, and I end up with an optimal basis for this modified problem, which is both primal and dual feasible for the modified graph. But I observe the condition to be primally feasible is simply that all of the flows are balanced, so supply and demand gets balanced, and I haven't changed my supplies from my original graph, and that all of the flow goes in the right direction, which is true because the basis is primally feasible for this graph. That means that this basis is primally feasible for my original graph too. So I know that if I take this basis back to my original graph, it'll be primally feasible, and I can start running the primal simplex method. And so I do that. I bring the basis back over, I recompute all of the dual slack variables according to the actual edge costs, I observe that the basis is indeed primally feasible, and I start my primal network simplex method. So my first entering arc is going to be the arc Fi, and that creates this cycle here. And so my leaving arc is going to be the arc Hi, which has the smallest flow in the opposite direction, the opposite oriented edge with the smallest flow in the cycle created by my entering arc. And I'll assign 1 unit of flow. I'll take the unit of flow off of this and assign it over here. And now I actually am already at the optimal solution. As it turns out, the optimal solution, the cost is 302, and it's this one. And I did that by way of a dual first two-phase method. Okay, so one more example. We've got to try the opposite case. Starting again from that infeasible basis, let's use a two-phase method with the primal simplex method first, then the dual simplex method to solve this network flow problem. So my goal is to do anything necessary to make this basis primal feasible. And I figure, well, the only reason it's primal infeasible is because of an imbalance of flow, so I set every vertex supply value to 0. That forces every flow value to be 0, which of course makes the basis primal feasible. Now I can use the primal network simplex method, I can run primal pivots, and when I'm done, I will have a basis that is both primal and dual feasible for this graph. And because the conditions for dual feasibility are the same in this graph as they were in the original one, the basis I end up with will be dual feasible for the original graph, and I can carry it back over, and I can then start running dual pivots on that. Okay, so my first primal pivot is, again, the entering arc is Fi. That creates this cycle. There's going to be a tie again. And so what we'll do is, again, choose the alphabetically smallest arc. Because we have a lot of choices, we'll choose Ag. Okay, there we go. The total cost is 0. That's nice. We're shipping no flow, so of course it costs nothing. And you can see now why detecting unboundedness in this case is a bit weird. We have to use different fake supply values if we want to make sure that in certain cases to make sure we can detect the right kind of unboundedness, because this objective function is never going to change. Okay, so I perform another pivot. It turns out actually this is the optimal, already the optimal basis for my modified problem, and therefore it is going to be primal feasible and dual feasible for this modified graph, which means it is dual feasible for the original graph. And so I bring it back over, I transplant it into my original graph, and I end up with a very, very primally infeasible basis for my original graph, but it is dual feasible. I can now run the dual network simplex method. So I choose a leaving arc. I'm going to choose the arc Hi. That separates us out, so this will be my component C1 in this case. I now want to choose the arc that enters C1 that goes, well, I want to choose as my entering arc the arc that points into C1 with the smallest dual slack value. I think that has to be Ag, which is sort of amusing because I did just pull Ag out of the basis, I think. Okay, so my entering arc is Ag. I'll transfer the flow to Ag. I'll take a look at my result. At the end of iteration 1, let's see, I've got a total cost, not that it makes much of a difference. I have a total cost of 134, and I still have some primal infeasibilities. I will choose one of them as my entering arc. I'll choose the alphabetically smallest for lack of any other ideas. That'll be AB. That separates my graph into these two components. There is C1. Notice that the leaving arc is BA. It points out of C1. So I want to choose an arc pointing into C1. I think this is the only choice as my entering arc. Yep, there it is. I will assign the flow. I will do the pivot, recompute. I'm still not done. I still have one primal infeasibility. Okay, so in this case, my leaving arc is going to be CD. We've actually sort of seen this case already. D gets stuck in a component by itself. We want to choose an arc with among the arcs pointing out of the component, choose one with the smallest dual slack value, which in this case is going to be the arc DF, which has 31. We will choose that. And we'll assign flow to it. We will perform our pivot, and then we will get to and it turns out this is the last pivot that we need. We perform the pivot, and we end up, after our two-phase primal first method, at the optimal solution in the last slide of the course. And I think we can all agree, this slide or any other, that the real optimal solutions are the friends that we made along the way.